So I mentioned many times that signal amplification is very much necessary to detect very low level of analyte or biomarker or target. So how we can amplify the signal, right? So this is very important things. What is the signal to background ratio? And in the biosensor, how we can modify the surface so that our signal will be very high and background will be very low, and how we can choose the material of the electrode. Now we are coming this point. Hmm. How we can choose the material and how we can think about the signal to background ratio. Hmm. So signal, this is signal, and background means B. So S by B. This is the very common term we are using for a ultra sensitive biosensor. So this one should be very, very high value. So the main important keyword for the signal amplifications is the redox cycling amplification. So I already told you many times that the reduction and oxidation reaction, right? So, so these two will be combined together, redox cycling. Reduction and oxidation will be combined together, and it will help to generate the higher signal and modification of the surface. So we can modify the surface with different kind of nanomaterial that I already taught you so that we can amplify the signal. So today actually I will focus on mainly the redox cycling amplification. So let's come to the point. So how we can use this one for a ultra sensitive biosensor. See, you can see in the medical diagnostics, there are few challenges, right? So one challenge is the quick detection, right? So when you are getting the sample from the patient, uh, so if you can provide them the result within a few minutes, even within a few seconds, that will be the better technique than waiting for a whole day or few days. Actually, it is very common practice even in the hospital or in the diagnostic center also. Hospital, they take a long time because of too much load. And in the private hospital diagnostic center, if you pay, we are paying lots of money, but still we have to wait for the result, right, students? So do you have any experience that you sent your sample and you are waiting for a few days for getting the result, right? Mm-hmm.
Yes, sir.
Yes,
So,
sir.
so this is the very common problem. Hmm. So how we can solve this? So this is, so that one question, that's why in the biosensor, very big question mark, that is the quick detection. This should be implemented on your sensor device. And another technique is called on-site detections. As I mentioned, that generally the expert, I mean some expert people, right? Some doctors or any kind of nurse, they're taking sample from you. So you don't have that kind of expertise so that you can do by yourself. That is a gap still we have. So on-site detection is possible only when laymen or common people, they can do by themselves. Then only it is possible. So we have to develop some biosensor that on-site detection necessary. And third point is the ultra sensitive biosensor. So why we need the ultra sensitive? Ultra sensitive, we can develop a biosensor where signal to background ratio is very, very high, so that we can go very low level detection, right? Low level, very low, around femtomolar or picomolar detection. This much we can go, we can achieve. But this answer is almost constant, almost no. Few devices are available, just for glucometer, pregnancy test meter, but they have still some drawback. But for the other kind of disease, like different kind of cancer, different kind of other infectious disease, some viral kind of disease, so we don't have such kind of sensor device. So that's why it is a big area. Still, we have this gap. So it is very much interesting area, so that we can develop some sensor device for point of care. POCT means point of care testing. So we should develop something this. So that can be achieved if we can develop some ultra-sensitive biosensor whose signal to background ratio is very high. This is for ultra-sensitive, and thus we can miniaturize by using our electrochemical technique that I already told. So today we will focus on how we can amplify the signal S by B, signal to background ratio. This is number 3 topic. So this topic, ultra-sensitive detection, today we will discuss how we can develop. So this is our main focus. Amplification. So I told many times that we are using many chemicals, right, in the biosensor surface. Just take it very simple way. Don't think that we are not, or maybe all you are not from the chemistry background. It is fine. But I will tell you some very simple, very basic chemical structure or chemical name. But no need to remember all the things, but you should understand the technique. How the chemical actually help you to generate high signal to background ratio. Just understand the technique. So you can use not only the chemicals that I'm going to show you, you can use similar kind of chemical, or you can think about how we can change the chemical. I mean, not only that chemical, how we can change it. Means you can maybe use some new chemicals also for signal amplification. That I will show you. See, as I mentioned that this is the sensing surface, right? On the sensing surface, when your primary antibody attached, so your biosensor ready, and you are adding your target solutions, and this is your target, it will be attached. So you have to detect this concentration of the target, right, guys? This target concentration you have to detect by electrochemically. So that is our main goal, electrochemical way. Electrochemical way we will detect. See, there is some way we can detect. So as I mentioned, we can use some secondary antibody, right? Secondary antibody can be conjugated, some nanomaterial, or secondary antibody can be conjugated with some enzyme. So some substrate will react with this enzyme, will form the product. Now, this product can be oxidized on the surface, on this sensing surface. So this product can be directly oxidized, and it will release the electron. So if we apply some oxidation put, suppose we are considering oxidation-based biosensor, right? Oxidation-based biosensor will apply some positive potential. So when you apply some potential, maybe this product can be oxidized and will form some other, after oxidation it will form other product and will release the electron, right? That electron will measure. So this is the very simple technique. But how we can amplify so that this electron transfer can be much faster, so that if we can make this electron transfer rate very fast, so that our signal will be very high. So signal will be high, and background, how we can make the background low. So in this case, background is the substrate. Substrate is the responsible for the background. So if your this tag and this one secondary antibody not there, secondary will be absent if target is absent, right? Then substrate will not react with this label and it will not form the product. So substrate S is responsible for the background. So if target is not there, so only substrate will be there, no P will be formed. So S will be responsible for the background. Clear, guys? Is it clear? Which one is responsible for background?
Yes, sir. Yes.
Hello?
Yes, sir. Yes, sir. Clear.
Right. So
Yes,
S will be responsible for your background. Okay, now you can see the star. This is for redox couple. So one redox compound we can use, like iron, as I said, maybe iron 3 plus. So iron 3 plus APCN whole 6, 4 minus 3 minus, as I told you. So maybe iron is an oxidation state 3. So we can use some iron based compound, right? So this compound, if it can react with this P product, this P, here P forming, right? If target present, then the secondary antibody will bind on the surface and this label will react with the substrate will form P. So if P again can react with the star. Star means some metal based compound, that is called some redox compound. So if they react with this redox compound, and it will form some cycling reaction, some redox cycling reaction. I mean, oxidized product can goes back to reduced product, and that reduced product again will react with the surface, will release the electron. So by these cyclic reactions, we can make the electron transfer rate much faster on the surface. So when substrate, only substrate there, no redox couple present, I mean no iron compound present on the surface, then the electron transfer rate from substrate to the electrode surface, maybe you can think about that electron transfer rate if it is R1, and if you have some redox couple like iron compound, and if they couple with this P, that time if you think about the electron transfer rate R2, actually this R2 will be much faster than R1. Means if you have some redox couple, means very iron something like iron or osmium based or ruthenium based, there is so many redox couple is possible. I will teach you again. I already told you that potassium ferrocyanide can be a redox couple. So if they react with this product, that time the electron transfer rate can be much faster because of cyclic reaction. Because of cyclic reaction, this electron transfer rate is much faster. Because of the electron transfer rate much faster, so your signal, so signal means which one is responsible for your signal? Because your secondary antibody conjugated with some label, and this is substrate transformed to the product P, and this P will release the electron by the help of some redox mediator. So this is called some mediator. What is mediator? This is called redox mediator. So why redox mediator? Because Fe, suppose this is 3, right, and Fe2. So they will not change their concentration, but they can be interchanged together themselves. They will be interchanged. So their concentration will be fixed. They will not be changed, right? So this is called mediator. Why it is mediator? Because they are helping the transfer of the electron from substrate to electrode surface. That electron transfer rate they are helping basically. That's why they are the mediator and catalyst. They are not changing, but they are helping the electron transfer from substrate to the electrode surface by a cyclic reaction. That's why this reaction is called redox cyclic reaction. Redox cyclic reaction. So if you can incorporate some redox cyclic reactions on a biosensor surface, then your electron transfer rate will be much faster. Your signal will be much higher than without redox cycling. Clear, or can I repeat one more time?
Please repeat.
I can't hear you.
Hello,
Hello?
hello, sir.
Tell me.
Sir, repeat this thing, please.
Okay, let's come. See, so this is your sensor surface, okay? And your sensor surface, you already add your target. So target bind already on your primary antibody, right? Now you add the labeled and secondary antibody. So this is antibody 1, this is antibody 2, that is already labeled. Now,
Uh, hello, sir.
tell me.
Sir, in my network problem, I joined late. Sir, please tell why sensing surface
Why sensing surface?
used in here.
Why sensing use? See here, sensing surface just a transducer is helping to bind your primary antibody and thus to form the biosensor.
Oh,
So this is just a transducer, sensing surface.
okay.
Just sensing surface is helping to bind your primary antibody. Now I will teach you how we can choose the sensing surface, the material of the sensing surface. That's one also I will teach you today. Just wait. So here, primary antibody, that already bind with your target, and we add the secondary antibody, the step by step after washing and washing. Each step we are washing, then secondary antibody, and substrate always will be there, right? In zero case or target and zero, both case S means substrate. Substrate means you are using some starting reagent that will react with your label or anything means on your your sensing reaction. For that we are using some reagent. That reagent is your S. Clear? So S is your starting reagent that you are going to incorporate in your sensing surface that will help you to generate the signal. See, if your target not present, then the labeled antibody will be there or not?
No, sir.
No, right?
Yes, sir.
No. So labeled antibody will be not there. So you will have only S and the star. Star is that, as I said, star is a redox, some redox, some redox mediator or some redox material. Suppose FeCN whole 6. This is K4 FeCN whole 6 or K3 FeCN whole 6. So here iron is oxidation state 2, here iron oxidation state 3. So some iron based compound that is called the electron mediator. Why they are saying the electron mediator? Because during the reactions, their concentration will not be changed, just they will help to transfer the electron from substrate to electrode surface, your sensing surface. Okay. So if there is no electrode mediator, then if substrate will react with this and form the product, and this product can be oxidized on the sensing surface, and this electron basically will measure, right? So which electron will measure? When substrate form a product, and that product will be oxidized on the surface, and electron will be released. That electron will measure, right? Clear? Hello?
Sir,
Mm-hmm.
sir, the previous statement, you said that electron mediator helps to transfer electron from substrate to the electrode surface.
Huh.
Sir, how is it possible? Because our aim is to generate high signal to background ratio.
Right.
Sir, so this reaction should be prevented, or just we are encouraging this reaction to occur?
See, I will clarify you. Yeah, that's I'm saying. I'm going to repeat again and again. Huh? See, as I mentioned, S is the substrate that is your starting material, right? Your Vibhuti or
Bhupendra.
your Bhupendra. So your Vibhuti and Bhupendra voice is too much similar. Anyway, I can't
Okay,
see
sir.
you because I am just open the slide. I can't see your name.
Okay,
Anyway,
sir.
see, S means substrate, right? This is your starting material. See, one fundamental thing I will tell you today. So the criteria for selection of a starting material is like this, so that it will not react very fast on the sensing surface. If it react very fast on the sensing surface, can you imagine then what will be the problem? What will be the problem?
So it will generate high background signal.
Right. So it will generate high background. So we are considering S should react on the sensing surface very slow. Huh? But when S will react with the label antibody, will form the product, this product actually will react very fast. Means this product nature. That's why the selection of the reagent is very crucial part. Okay, selection of the reagent is very crucial part. It is not like this randomly. Let's use this compound and make a good ultra sensitive biosensor. It is not like this. We have to very carefully select a starting reagent so that it will not react on the sensing surface on the, I mean, it should not react, or it is not possible fully 100% to stop the reaction, but there will be some reaction. That's why we are getting some background. But this electron transfer rate will be very slow. But when this S will react with this label antibody and form the P, this P nature will be like this. It will react very fast. Clear? And
Yes,
this
sir.
P can couple now. So if there is no redox cycling, then we can measure just directly electron transfer from P. So basically you are getting P from the AS, right? That's why I'm saying the electron transfer rate from AS to electrode. So if there is zero concentration of the target, I mean no target, then from AS to electron transfer rate to electrode is very, very slow. Clear? Right? Bhuti?
Yes, sir.
Is very slow. If there is no P means very slow. Now if there is P means you are getting electron indirectly from the AS. So if there is product P, then P, when if there is a target there, then S will convert it to P, and then P will react very, very fast on the surface, and you will get the very much, I mean the very high electron transfer rate. So your signal will be very high. Okay. Now, if you can couple this P with some redox mediator, this star, then this electron transfer rate will be much faster than only P. Clear? Clear now?
Yes, sir. Yes, sir.
Okay, so if you can, so this is called a redox cycle. So redox cycling will help you to transfer the electron basically from S to electrode surface. It will be much faster. Okay, so okay, so I'll show you again.
Sir, so just
Yeah,
one doubt.
tell me.
Uh, this is for ultra sensitive biosensor. So that means ultra sensitive biosensor means it should have very low detection limit. How does detection limit come into play for with the redox couple this thing?
Yeah, so I'll show you one example, then you can understand. Huh? So it is right for you. Means it is very low detection. I mean the detection limit that I taught you, detection limit will be very, very low, very low. Hmm? Okay, very low means I told you, I mean 1 femtomolar or picomolar, something like this, very, very low. Hmm. So I'll tell you one basic example after this slide, and then it will be very much clear to you. So the substrate will form so many products. So this product will couple with this mediator, and this electron transfer rate will be accelerated. Okay. So fast electron transfer rate and very much fast, you can say very fast kinetics for this biosensor. Okay. So this is called one kind of chemical amplification. Why chemical? Because we are using some chemical reaction. So, so there is only product P. It can be easily only, it can transfer the electron. But instead of this, we are using some redox couple so that they are reacting with this. P will reacting with this redox, and some chemical reaction happen on the surface. So that electron transfer rate will be much faster. Kinetics will be much faster. So that's why it is kind of chemical amplification. So redox cycling basically redox cycling, so basically a chemical amplification. Clear? Guys, is it clear? Hello?
Yes, sir. Yes, sir.
Okay.
Yes, sir.
Okay. So let's go. So I'll tell you some basic example now, so that it will be clear more. So let's go the next topic. Next topic is the how we can choose the electrode material. Then we'll combine together. Then I'll give you one example of the redox cycling reaction. Okay. Okay. So as I mentioned, that substrate. So it is very much crucial part choosing this kind of starting material. So as I mentioned, that starting material should not react with your electrode surface very fast. So it should react very slowly. Means this electron transfer reaction. So if there is no target, as I said, so this secondary will not be there. So substrate should react on your surface very, very slow. So this electron transfer rate should be very slow, kinetically very slow. So but when substrate react with your label antibody and it will form some product, so this reaction should be very fast, right? See here, step by step I will teach you now. So substrate from the product, so this reaction should be fast. This is first criteria. But your other interfering species, as I mentioned, your sample contain oxygen, your real sample can be some other A means some other interfering species like ascorbic acid, right? Vitamin C, ascorbic acid, or uric acid, or some other material that present in the blood sample or urine sample or sweat, that is called interfering species, right? They should react on the sensor surface very slow. So this electron transfer rate will be slow. Oxygen electron transfer rate will be slow, but your product reaction on the surface should be fast. This is our criteria to generate high signal and low background. So how we can make this one? So we have to choose some sensing material so that we can avoid the unwanted reaction. So what is the unwanted reaction? That is interference reactions like ascorbic acid, uric acid, other material present, or oxygen reaction on your sensing surface. That is unwanted reaction. They should be very slow, and your main substrate that reacting with your label antibody, if target present there, then only you will get the label antibody, and it will form the product, and this product should react on the sensing surface very fast. It is the main criteria to develop an ultra sensitive biosensor. Is it clear
Hello,
this
sir.
point? Yeah, tell me.
Hello, sir. If P is oxygen product, then electron on electrode it is fast or slow.
If P
Is oxygen product, sir.
oxygen product.
Yes.
No, this P will be see let's give some example. If S means something like you can say like as I mentioned last time, some nitrophenol NO2, right? NO2OH, some nitrophenol. Huh? So this nitrophenol, when it will react on the surface, then this reaction is very slow, no reaction almost. So on the electrode surface, reaction almost no or very slow reaction. But if it is some target present, then this nitrophenol can be converted to the aminophenol. Aminophenol means this. So it is not like oxygen product, it is some product that is very, very reactive on the electrode surface. So this kind of not, it is not kind of oxygen material. So oxygen, I am saying, if it is present on your solution, so then there will be some side reaction. But an oxygen reaction zone also I already taught you, right? So in the high positive potential, it can be oxidized, and low negative potential, it can be reduced, right? So you should use, that's why this region, as I mentioned last class, right? You cannot use very high potential, so the oxygen can be oxidized. You cannot use very low potential, negative potential, because oxygen can be reduced. Can you remember this one?
Yes, sir.
So you have to use, that's why this window, this potential window, this is called potential window. So this potential window you have to use, that I already mentioned, right? So you have to avoid this oxygen reaction. You have to avoid this interfering species reaction. And that's I said, you have to use some material so that it will form some product like this aminophenol. So this aminophenol reaction on the surface is very fast. So I will tell you again some chemical name that can be used as a substrate. So how we can avoid this? So first thing is that we can use some less sensitive material, not too sensitive. Like if you use a gold plate, gold or platinum, they're highly electrochemically active. They're very high, they have very high activity. So oxygen and other interfering species can easily oxidize on the surface in the low potential window. I mean, they can merge in the lower area. I mean, here. So that you are considering your potential window applicable for your biosensor. Now, if you use like a very high, I mean, the that is electrocatalytically active material. That is called gold, electrocatalytically very active. Platinum, they are very, very active. So that oxidation range can come this region, means your potential window region, they can merge. So in this case, your oxygen reaction, your intermediate species reaction can possible. So in this case, your background will be very high. Okay. So you have to choose such a material so that your this kind of unwanted reaction like oxygen should be avoided, right? So how we can choose this? So you have to choose a material so that, I mean, some less sensitive. It is called less sensitive or less catalytically active. Or less sensitive means less catalytically active. Catalytically means here always I am saying electrocatalytically. Here electrocatalytically in bracket electro. So electrocatalytically it should be less sensitive, so that we can avoid this kind of interfering reactions. So for the ultra sensitive biosensor, it is very, very important to choose a sensing material where we'll get very fast reaction, that is called the wanted reaction. So can you tell me which one is wanted reaction, which one is unwanted reaction here? Guys, tell me which one wanted reaction here?
The one with oxygen and ascorbic acid are unwanted reactions, and the
Yeah,
one with a product using the redox couple are wanted reactions.
yeah. So this is wanted, right? And here is the unwanted, right? This region. So this is your left side is the wanted reaction. So this reaction should be fast, right? Right?
Yes, sir.
And right hand side, this reaction should be slow, right? So this fast reaction is responsible for your signal, and slow reaction is responsible for your background. So your S is very, very high than your background. So your S by B ratio will be much higher. Like this, so you can get a ultra sensitive biosensor. Clear? Clear?
Hello, sir.
Tell me.
So, won't this redox couple increase the speed of the reaction for O2 and A also? Like,
Uh, please continue. Please
sir,
repeat.
sir, the redox couple can increase the rate of reaction for O2 and A also.
Right, right, right. What is your name?
Akshat.
Very good question. Very good. Your background chemistry or chemical?
No, sir, instrumentation, sir.
Instrumentation. But your question is very good. See, as I mentioned, we are using some redox couple, so they can accelerate the reaction, your wanted reaction, right? They can accelerate. So at the same time, they can accelerate the unwanted reaction also, like oxygen, these things. But as your means you have to choose some applied potential that I means that I told you, right? So you have to optimize like 1 2 3 4 5 6, so many potential you have to apply. Then you have to optimize which potential region you are getting higher signal to background ratio, that is your optimal applied potential. Okay, sir, clear?
Yes, sir.
So that potential you have to optimize. You are very true. Means as you wanted reaction increasing, at the same time unwanted reaction also can be increased. So in which potential you are getting, this is the highest and this is the lowest, that you have to optimize. So you have to, in this whole region, you have to apply 1 2 3 4 5, like all the potential you have to apply. Then you have to find out which one is the best one. Clear?
Sir,
Okay. Tell me.
sir, sir, for the different kind of substrate to product reactions,
Hmm.
we'll use the different kind of redox couple, right, sir?
Right. That is also correct. So when you are, if you change the substrate, then you can change the redox couple, or sometime you can use the same redox couple if they react with the product very good way. And if the reaction rate like P plus redox couple, right? So they should react. If this reaction very fast, so you can use. If this reaction slow, then you cannot use. Then you have to change the redox couple, or you have to, maybe you can change the substrate so that P also automatically will be changed, right? Clear, right? Okay, clear now?
Sir,
Yeah. Tell me.
sir, what is the criteria of this choosing the redox couple with respect to our substrate?
Okay, that I will come when I will give you some example. I will come. Let's wait. Let's wait. See, so now come to point step by step. So I will. This is a very important parameter, important topic. You will not get in the textbook like this way to describe step by step. But in this class, actually, I will teach you and I will share you some research article basically, so that you will get the whole practical knowledge how you can use this redox cycling reaction for signal amplification. I will share some journal with you after this class. See, so say if Fe2 plus oxidize, then it form the Fe3 plus, right? This is called oxidation, right? Fe2 plus, if release electron, if this accept one electron, then Fe3 plus convert to Fe2 plus. This is called reduction. So if this oxidation and reduction happen same time together at the same reaction, then it is called redox reaction, right? So let's show you. Now I'm going to give you the example. Concentrate, very carefully concentrate here now. See, this is a full biosensor, full sandwich based on sandwich biosensor that completed. That I'm not showing step by step washing these things. The step will be like this, like primary antibody IgG. IgG, your primary antibody, AB1 primary antibody that captured one cancer biomarker CA125. This is a cancer biomarker that attached on your primary antibody. Now, if this target there, CA125 your target, your biomarker, then your secondary antibody attached on the surface, right? So this is, I already told you, so I'm not repeating again and again. So this is just your complete sensor surface. Now, your secondary antibody that conjugated with GOX, that is called glucose oxidase. Glucose oxidase. This is one enzyme. So glucose oxidase is one enzyme that this enzyme, see, enzyme is a very, very specific. It is called kind of catalyst. Only specific substrate can react with the enzyme. So if you use here uric acid, so this uric acid cannot react with here. But if you use the glucose, then glucose can react with the glucose oxidase. So it is very much specific. Okay, so that's why we are using some enzyme, means we have to use some specific substrate. So which substrate then I will use here in this biosensor? Which substrate I will use? Tell me.
Glucose based.
Glucose, right? So we'll use here glucose. So like this way, we can select the substrate name. So we cannot use here any other substrate. So here glucose is a substrate. So this glucose will react with glucose oxidase and it will form a gluconic acid, some product it will form, and it will release the electron. So this electron we have to measure. This electron will transfer to electrode surface, this electron. So if this is fast or slow, see, this electron can be transferred easily and we can measure if we apply some potential like 0.3 volt. If we apply and if we measure the chronoamperometry, then we will get a like current versus time. We will get something like this, right? If we apply some potential, we will get something like this chronoamperometry. Now, I am going to show you now how we can make this reaction faster. So here we can use some mediator, some redox couple. So what is the redox couple I am going to use here? Ruthenium, Ru. Ru means here ruthenium hexaamine. See here NH3 means amine group, 6 amine group there. So So it is called ruthenium hexaamine. 3 plus means here ruthenium oxidation state 3. Clear? So ruthenium hexaamine is kind of a redox mediator. So this is available. We can easily buy it. So ruthenium hexaamine 3 plus actually can react with this electron. That will means this ruthenium hexaamine will help to transfer this electron to the electrode surface very easily, much faster way. And it will convert it to the ruthenium 2. Means it will accept the electron as electron is present there, right? So it will accept the electron, ruthenium 3, and it will convert it to ruthenium 2 hexaamine. Now, when you apply some potential, like 0.3 volt you are applying, right? At this potential, ruthenium 2 will be oxidized again, and it will convert to ruthenium 3, right? So this is kind of cyclic reaction. So you are using ruthenium 3. So your starting material is the glucose and ruthenium 3, 1 and 2. So these two mixture is your starting reagent. Now, if glucose oxidase is present, then glucose will react with the glucose oxidase, and that electron will go to ruthenium 3, and ruthenium 3 will convert it to the ruthenium 2. And as we are applying some oxidation based potential 0.3 volt, at that potential, these two will be converted to again ruthenium 3, and this electron will be transferred to the surface. So basically ruthenium 3 is kind of mediator, because see, it is actually interchanging 3 to 2, 2 to 3, 3 to 2, 2 to 3, like this way. But it is getting the electron from glucose actually, right? Ruthenium 3 getting the electron from glucose. And that glucose can release the electron if glucose oxide is present. And that electron come to the ruthenium 3 and convert to ruthenium 2. And ruthenium 2 again convert to ruthenium 3 by when we are applying some potential. So basically ruthenium 3, ruthenium 2, this couple helping the electron from glucose to the electrode surface. And this mediator actually helping much faster way this electron transfer. So if this couple, this ruthenium couple not present, then this, if we measure the kinetics of the electron transfer rate from glucose to the electrode surface, it will be very slow. It will be very, very slow. Means this kinetics. This is if kinetics 1, K1 is the kinetic 2. So K2 is very, very high than K1. So K2 means if ruthenium present, your electron mediator present, then electron transfer rate will be very high. Make it clear, guys. This is the very simple redox cycling reaction. If it is clear, then next other reaction, all the sensor will be clear. Then we will go slowly in the complicated. I mean, we'll go more complex biosensor. Slowly, we'll enter. So let's simplify this one. If it is clear, then we will go to the next biosensor. Clear, guys? Or can I repeat it again? Hello?
Yes, sir.
I can't hear you.
Sir, yes, sir. Clear.
Clear, right? So
Yes.
I'm repeating again and again because this is very fundamental thing you have to understand first. So if it is clear, then I will go fast because you can understand all the biosensor very easily. That I will go give
Hello,
show you some sensor
sir.
device. Yeah. Who?
Sir,
What is your
I
name?
have some questions, sir. Suman, sir.
Suman. Okay, tell me, Suman.
Sir, can the redox cycling rate, the mediator, can it make maximum reaction rate, or it can be maximum more, or some other reason? Uh, I think my question is, it is the maximum, or it can be more, can rate can be make more
I
faster?
mean, maybe we can change it. Maybe we can make it more faster. I mean,
Yes.
more. That you are asking. Okay.
Yes.
That is also I can answer you. See. Yeah, that is also very good. You can keep asking the question. That is also good thing. See, so it means if you want to make this reaction much faster, then maybe you can optimize this material. This electron transfer material you can optimize. So instead of using ruthenium, maybe you can use some osmium base. So if you go to the periodic table, so you know the periodic table, right? Periodic table, you know. Hello.
Hello.
Yeah. Do you know the periodic table?
Yes, I forgot, sir. I have physics student.
Yes, sir.
Yeah. See, I am going to show you. See
Yes,
the.
sir.
So that's I'm going. That is very good question you asked. Means how is it? I mean highest reaction, or we can change it. So that's the things I'm going to teach you. Means we can select the material like this way, so that we can improve basically our biosensor. See, periodic table. I'm going to share one table here. See, you can see the periodic table, right? Is it visible?
Yes, sir.
See, this is called actually. I'm not going to tell you all the details, just for your basic information, so that you can understand. So in this is the series, and this is the column. So in this column, you can see there is so many material. I mean, this is called transition-based material, like iron, ruthenium. Fe means iron. So as I mentioned many times, we are using Fe, means iron, potassium ferrocyanide, potassium ferricyanide, or ferric chloride, ferrous chloride. So iron-based material we can use. Ru, means this is ruthenium. So ruthenium 3 and ruthenium 2, these two oxidation state possible. So these things also we can use. Osmium, Os. So this thing also we can use as a electron mediator. So not only this, if you go to the next column, Co means cobalt, RH, IR. So this kind of material actually very commonly used in the sensing material as a electron mediator or redox couple. This kind of material people are using. Why they are using? Because they have some very good property as an electron mediator, and they can easily accept and release the electron. And this is some kind of reversible reaction. I mentioned many times. So they are very fast reversible reaction when they can accept and release the electron. This material. So Ap, Ru, Os, Co, Rh, Ir, this kind of some this metal based some complex you can use. So if you think maybe Ru is not good for this biosensor, you can change it. You can go for Os. You can go for Co. But then optimize or calculate the reaction rate. Calculate the signal to background ratio. Which one? Higher. So if you are thinking that now OS is better than RU, then go for OS. So like this, so you can optimize. Clear? Got your point?
Sir, I have one question.
Tell me.
Sir, actually, so far what I know, correct me if I am wrong, that it depends on the potential which we are applying. Because if suppose we are choosing an element osmium OS, and if we are applying the potential of around zero point 0.2 volt, suppose here you were applying 0.3 volt, and if oxidation or reduction couple they have also their own, then if we are not providing that much of potential, then the redox couple will not take place.
See, like this here, osmium, your oxidation reduction potential happened here, right? In iron case, it is happened here, right? So osmium case, generally we are getting better result. Why? Because oxidation almost completed in this region, right? This potential, and you can avoid almost all the interfering species, because interfering species are oxidizing in this region. So that's why if you think you can change your iron-based material to osmium-based material, it will help you. Definitely. So like this way, you have to actually optimize which material is better. Generally, I can say, practical like this situation. If you change the material iron to osmium, you will get very I mean, you get the better result. That I can assure you. Okay.
Okay, sir.
So like this way you have to calculate. See, so let's come to the point now. So this is the actually see. So what is the starting material in this biosensor? Glucose and ruthenium 3. So we are not going to use ruthenium 2 as a starting material. Can you tell me why? Tell me why we are not using ruthenium 2 as a starting material. We are using ruthenium 3 and glucose, not glucose and ruthenium 2. Why?
Because
Then it will take the electron.
yes,
Right.
Because we want to oxidize the glucose.
So it should, because see, glucose already oxidized on the glucose oxidase surface, so it has the electron. So someone should accept this electron, right? So ruthenium 2 already reduced form. This is already reduced. So which one is already reduced? So uh, is it possible to accept this electron? No, it is not possible. So only ruthenium 3, it has the capacity because higher oxidation state. So higher oxidation state element can accept the electron, right? So it will accept and it will be reduced. That's why you have to use here some higher oxidation state material, not lower oxidation state, because you already have some electron that should accept. Now you are going to apply some oxidation potential like this. So oxidation potential means you are applying some potential, electron will be released. So that electron we can measure. So here ruthenium and ruthenium 2, ruthenium 3, they are the mediator. They are basically helping the electron transfer rate, and they are not changing. They are mediator and they are electrocatalyst. This is called electrocatalyst. Okay, so now I can show you this graph, chronoamperometry. So if the electron mediator or ruthenium not present, then you will get like this. And if present, then you will get very high signal, very high signal you will get like this. So it is current versus time. You will get very high current if this mediator present. So this is kind of the cyclic reaction, right? And we are saying this one redox cycling because reduction and oxidation happen, and this is cyclically happen. See, we are applying potential, so it is converted to 3, 3 can convert to 2, again 2 to 3. So this is the cyclic reaction happen repeatedly. So this is repeated reaction, right? Repetition. So because of this repetition, we are saying cyclic reaction, and full name is called redox cycling. Clear what is redox cycling?
Yes, sir.
Okay, so this is very simple redox cycling. Now we'll go some complicated one. So here somehow we got signal to background ratio maybe x. Now someone someone just asked me, how can we improve it? X, can we go to x to x1 so that x1 will be much better than x? Yes, we can go. We can go. Let's see how. Okay, so just one thing. So here in this redox cycling, we can give a name. So now we are going to put some nomenclature. So as I said, we can go some many redox cycling reaction to how we can get much faster, right? So our ambition, our goal to make the cyclic reaction much faster, right? So here maybe reaction rate x, maybe we can go x1, then again we can go x2 by changing the material. So how we can make them? X2 much higher than x1, then x1 much higher than x, how we can make them? So that's why we'll go more complicated redox cycling reaction. I mean, we will add some extra chemical. So we will give accordingly some nomenclature of this redox cycling. So this redox cycling is called enzymatic redox cycling. So why we put the enzymatic redox cycling? Because we use some enzyme here. This enzyme, this is glucose oxide is the enzyme, right? And it is reacting with a single redox couple, and it's forming some redox cycling reaction. as enzyme is helping this redox cycling reaction, it is called enzymatic redox cycling. Clear? This is one nomenclature. Guys, is it clear?
Yes,
Hello?
sir. Yes, sir.
Yeah. Okay. Now let's go the next one. Other nomenclature. So enzymatic redox cycling, it is called, it is we'll go some abbreviation. It is called EN. EN means enzymatic redox cycling. So we'll give the short form now. Slowly. EN means enzymatic. It is enzymatic. So this is just I taught you this one. R means some substrate, means just for example like glucose. It will form a gluconic acid, right? So here P. So here actually we are using which material? Q we use, right? Ruthenium 3. Q is the ruthenium 3, right? And P is the ruthenium 2. And it will be oxidized, right? So we can express like this way, right? After I mean this slide, we will give some I mean say some abbreviations. We'll give some nomenclature or like this, so we can represent like O R P Q, like this will represent. Okay. So last time we used like this. So this is the enzymatic redox cycling. Now, so this P, how this P form, that I already told you. Now I'm not going to repeat again. By some label. So here, so it can form. So let's skip this one. Now I am coming. Now I am coming some other reaction. See NN. NN means so enzymatic. I mean we can use two enzyme instead of using one enzyme. Maybe we can use some another two enzyme. So it is called NN, enzymatic redox cycling. How? See, so we can use a substrate R. This is the starting material. It can react with one enzyme. It can form the oxidized product. So electron will be released, and see the electron is releasing, right? So this electron will go to this Q. So we are using some starting material Q. So this Q will accept this electron to form the product P. And this P can react again with some another enzyme 2, right? And it will form again the Q. And when this P will oxidize and it will supply the electron to O1. O1 means some another, maybe it is called some electron mediator. O1 some electron mediator, like some ruthenium 3, right? So ruthenium 3 will accept the electron and it will form the R means ruthenium 2. Okay. Now this R1, if we apply some potential, this R1 can be oxidized and will form the O1. So the first enzyme 1, enzyme 2, this is enzymatic, right? Two enzyme reaction. It is called enzymatic. Now, if we apply some electrochemical reaction, I mean you apply some potential like 0.3 volt, if you apply, then it becomes electrochemical reaction. So the full, this is the full one now. Full one is what? Enzyme means enzymatic, and last step electrochemical. So ENN means enzymatic, electrochemical, enzymatic. So ENN redox cycling means electrochemical, enzymatic redox cycling. As you can see here, one cycle, two cycle, right? So first time you can see only one cycle, but in the second case, this one, you can see two redox cycling reaction simultaneously happening on the surface. So if you increase the number of cycle, the electron transfer rate also will be much faster. I mean, if x2 and first time if you consider x1, so x2 will be much higher than x1. If you increase the number of cycling, the kinetics for the electron transfer rate will be much faster. Make it clear. Guys, is it clear? or I can repeat again.
Hello, sir.
Tell me.
Yes, sir, what is the difference between NN redox cycling and ENN redox cycling? Please once more discuss.
Number A and B. So A means NN in this case. So I'm okay. Just removing this thing. See, in N case, see only electrochemical part is missing, right? And ENN case, electrochemical part is incorporated, added. So E means electrochemical. Means NN case you are not applying the potential. So when you mix the chemicals on the surface, so up to here the reaction will start and stop. The reaction will not be completed, your cyclic reaction will not be completed, your redox cyclic reaction will not be completed, something like this you can say. But when you start measurement, your electrochemical measurement when you start, then you apply some potential, right? Suppose 0.3 volt you applied. Immediately this R1 will be converted to the O1, right? Because see, like a stair, you just cut down one step. That's why this is not completed. The full reaction was like in the frozen stage, it stopped. As you added this step, your stair is completed now. So electrochemical reaction actually started, then this cyclic reaction actually started, and full these two cyclic reaction now completed, and this reaction will be going on and going on the surface repeatedly. It will be continuing on the surface. Clear?
Sir, this notation, please, actually is quite confusing. ENN and NN. Please just write what is explain, not explain, just tell the notation what it is.
Okay. See here. See, E means electrochemical. Okay. Electrochemical. E. N means enzymatic. Okay.
Okay,
So
sir.
NN means enzymatic. It means here actually you are using two enzymes. See, enzyme 1, enzyme 2. Now, here actually E part missing because you are not applying any potential. When you add potential, now it become ENN. So basically, from here to here you are going. So NN to ENN you are going when you are applying potential basically. So ENN electrochemical, enzymatic. Now clear?
Yes, sir.
See, now I'll go some another part. One main drawback of using the enzyme, as I saying that yeah, we can amplify the signal, we can get very high signal because here you can see two cycling there, but here one cycling there. So if you increase the number of cycling, so electron transfer rate will be higher, much faster, right? That is the criteria how we can improve the electron transfer rate. But as you are using the enzyme in this biosensor, there is some drawback. Enzyme kind of protein, they can be denatured easily in the room temperature or at the higher temperature. So sometimes we are storing our biosensor at the room temperature, or even in the summertime. Think about in the rural area, generally don't have the refrigeration system. If you are going to use your sensor surface for common people, right? In the rural area, just think about the temperature. Summertime, how much? Think about in our West Bengal, southern part. How much?
40, 45 around something.
45. Yeah, sometimes it's 45 degrees Celsius. It's very difficult to store the enzyme in this temperature, right? But if you have refrigeration system, then you can use the enzyme, and it is very much specific. Why where people are using enzyme? Because enzyme is very specific. It will not react any other substrate, only specific substrate. Like glucose oxidase case, it will react only glucose, like this. But problem is it is kind of biomolecules. This kind of protein cannot be stored for a long time at the high temperature. So we should avoid the using the enzyme if you don't have the refrigeration system. That's why we are thinking in the develop some redox cycling reaction without enzyme. So that is called enzyme-less biosensor. Enzyme-less biosensor. So that is the main thing. So why we need enzyme-less sensor? Because the stability of your biosensor. Clear? This is very important point. So this is a biosensor here, right hand side. You can see here we are not using enzyme in this part. Here we are using only R. R is a reducing agent. Reducing agent. R is a reducing agent that will react with Q and it will form a product P. So basically, can you tell me the Q, the nature of the Q? It should be oxidizing agent or reducing agent? This Q, the nature of the Q.
Reducing agent.
Yeah, so it is actually oxidized form, higher oxidation form, right? It should be higher oxidation stage so that reducing agent can reduce it. So there is no enzyme, just we are using a reducing agent. Like I said, sodium borohydride, as for example, NaBH4, a reducing agent. So it will react with this Q, it will form a product P. So this is actually reduced form. So now this reduced form can easily oxidize on the surface when you apply some potential like 0.3 volt. It will release the electron. Correct? Correct? Yes. See, yeah. So instead of using enzyme, we can use some chemical and they can take part in a redox cycling reaction. So we have to use some starting material, some reducing agent. This is starting material number 1, and another starting material Q, right? And here we are getting, say, we are getting P. As I told you, we can use some S. S can help to produce the P. As I said, the P actually very much reactive agent, right? It can easily react on the sensing surface. So if you directly use P on your sensor, then your background will be very high. But if you can use a substrate, some starting material that can react with some your label, and how your label will come on your surface, if target present, then only your label will come, and your S will form P, and that P is the highly reactive one. It can react on the surface. So this label can be a nanomaterial, a nanoparticle, can be gold nanoparticle, right? And that gold nanoparticle or that label can come from the secondary antibody. Can you remember? Guys,
Yes.
clear? Clear? See, I'm now going slowly more deeper and deeper. Clear? So, like this way, we can make an enzyme-less biosensor. Means we can use this label like gold nanoparticle. Gold nanoparticle can react with the starting material S, some substrate, and it will form the P. And P is the, as I said, this will be highly reactive. So if it is not highly reactive, then you will not get high signal. Your signal to background ratio will not be very high. So first criteria, this P should react on your sensing surface very, very fast. And it will form the Q, right? When it reacts with the sensing surface, it will form the Q. And this Q should react with your reducing agent R very fast. Then only this cyclic reaction will be completed. This is the criteria of a non-enzymatic biosensor, and we can make it an ultra sensitive one if this product that form P from the S, if this reaction is very fast on the sensing surface, and the reducing agent that we are going to use that should react with the Q is very fast. So if this reaction very fast means Q and R, then only it will easily form the Q, P, right? Otherwise, this reaction, I mean here if this reaction becomes slow, then this cyclic reaction rate becomes slower because formation of P becomes slower. So if reduction happen very fast, then P will be formed very fast on the sensing surface, and that P will be then now oxidized on the surface material because of applied potential. Clear, guys?
Yes, sir.
See, it is very simple. Just clarify. Means make your basic strong. After that, you can answer all kind of the biosensor formation questions. How we can make a ultrasensitive biosensor? How we can choose the material? Which substrate is better for this biosensor? Which mediator is better for this biosensor? You can answer. So what will be the starting material in this biosensor? See, sorry. So in this case, we are using the starting material R, reducing agent, and S. This is the starting material, right? And right, this is the starting material.
Sir, S gets converted to P,
Hmm.
and then Q.
See the Q form, right?
Yes, sir.
So this is the starting material. So S is starting material, R is the starting material, right? Other is form in between, and this is called EC redox cycling. This is the abbreviation. E means, as I told you, E means
Electrochemical.
E means electrochemical. And here now we add another form, C. C means chemical. Chemical. So if I say EC redox cycling means electrochemical plus chemical, right? You can see in the electrode surface when you are applying potential, that is called E, right? As I mentioned the last time also, this is E, right? Because this is electrochemical reaction, we are applying potential. And upper one, the reducing agent converted to the that we are using a reducing agent, so that Q converted to the P. This is chemical reaction, right? This one chemical reaction, right? Right?
Yes, sir.
So see, so from the biosensor you can put the nomenclature. So this part is the electrochemical, and this part chemical, right? This is electrochemical, this is chemical. That's why this biosensor is called electrochemical chemical redox cycling based biosensor. Clear the nomenclature, guys? See, this is the redox cycling, right? That's why it is called EC redox cycling. Abhijit Desmukh. Hello, Abhijit. Abhijit, are you there? Hello? I can't hear you, Abhijit. Yeah, Abhijit, can you hear me? Okay, so is it clear? Everything fine? You can understand? There is some connection maybe. Okay. So if you want to repeat anything, any part, because this is a very fundamental thing, you should know. So if it is not clear, just let me know. I will clarify again and again, so that when we will come to the biosensor device design, so that you can answer basically. Yeah. So please tell me if it is not clear. Brotin, is it fine for you?
Yes, sir.
Okay, good. Devajyoti, Devjyoti, Devjyoti, are you there?
Yes. Yes,
So
sir.
is it clear?
Yes.
The nomenclature biosensor, right? Okay, good. Neil, what about Neil?
Yes, sir. It's clear.
Okay. Harshita?
Yes, it is fine.
Good, good, good. And yeah, so okay, then I'm not again asking. Then let's go to the next point. Don't hesitate to ask me if it is not clear. So I want at the end of this course you become an expert of the point of care device development of the biosensor. I want you should become an expert. It's very interesting course actually I designed for all of you. See, now let's come. As I taught you left hand side, see the left hand side. So it is enzymatic, then electrochemical, enzymatic, like two enzyme, right? So two cycling means much faster. Same way I'm copying here, right hand side. So here one cycling, so let's make it two cycle. Let's make it two cycle. So here one chemical reaction and another chemical reaction here. So two chemical reaction, right? So here one chemical and here another chemical, right? Two chemical reaction. Now we are adding these two chemical reaction with some electrochemical reaction. Now this going to be filled by electrochemical reaction. So on the electrode surface always electrochemical, and far from the electrode that is chemical reaction, right? So two chemical reaction are combined with electrochemical. So when it is only chemical, so it is called C and C. See, chemical. Now we are adding with the electrochemical. So what will be the name of this last one?
ECC.
Very good. ECC, electrochemical, chemical. So the electron transfer rate, if you think this one is X2 and EC if you think about X1, so X2 will be
Greater than X1.
not only greater, very higher. So I will show you some data later on. Even on when you will come to my lab one day if you visit. So I will show you X2 will be very fast. Only because of one extra cycling, you can make very fast reaction. So like this way, we can go ultra sensitive biosensors. That I am saying. So here, if you can detect picomolar, definitely ECC case you can go femtomolar level. Means if it is 10 to the power minus 12, so here you can go 10 to the power minus 15 level. In the case of ECC. This is the main fundamental things. How we can improve the rate of a biosensor. How we can design a ultra sensitive biosensor. Okay. So what is
Sir,
the redox cycling? Yeah, tell me.
sir, I have just small question. Sir, in CC, why are we? I mean, the below is ECC. I understand, but why are we just are not applying the potential here? Because we have to generate the high signal to background ratio, na?
No. I'm just keeping like this separate way so that you can understand how we are coming step by step. But this is actually we are doing all together, not like this. We are
Okay,
doing
sir.
together.
Okay, sir.
Number one plus number two, then become ECC. Okay. So we are not keeping like this. Just for your understanding, I kept like this way. Okay. So that you can understand how the step coming. Actually, what happened? Now I am telling you more details. I'm going to tell you. Okay, just nah, it is better to show you here. See, just think practically. So this is your sensor surface, your primary antibody coated, right? So this is your final sensor. You're going to detect something, some target. So target come, right? Now your secondary antibody come, that is labeled already. So you have to add some starting material. Just think about for the ECC case. So ECC case, what will be your starting material? Tell me now. Tell me the starting material for the ECC. The starting chemical.
The glucose.
No, in this case I already denoted, right? R, Q,
S
P,
S S S
SNR2.
S
R,
and R2. Yes, sir.
S and R2. Anything else? You are missing one more. See, in this case, from S, P is forming. So PQ you can generate from S, right? But what about O and R? O1, R1, right? So you have to supply. So which one you have to supply? O1 or R1? Tell me now. Which one you have to supply?
R1. R1.
R1.
R1, really? Really R1 you are supplying?
So R1 will convert to O1, giving one electron.
Yeah, that is when you are applying potential. But see, step by step, just I separated this one. See, that's when you asked me, that's why I told you I separated because of your understanding. You have to think about first the chemical reaction, then we are adding them with electrochemical reaction, right? So finally, when you will apply some potential, then your cycling will be completed and you will get the data. So before that, just so this is that's why I'm going to tell you the practical application here. So your sensor ready, you have to add some chemical here, your starting material, chemicals, not chemicals, your starting material you're going to add, and you have to incubate this sensor for a moment, like 10 minutes, you have to incubate. During the incubation, this kind of the chemical reaction will happen. And this cycling reaction happen and it will be stopped because you are not applying potential. When you apply potential, your cycling reaction will be completed and you will get get the data you will now obtain the data, signal data. Okay, so this is your incubation time. So your sensor ready, you applied your target that immobilized on the surface, you applied your secondary antibody that labeled, that is attached on the surface. Now you add some chemical and you have to incubate it for 10 minutes. Suppose you are incubated for 10 minutes. So during this incubation, this reaction will happen on the surface. Okay. Then after that, you have to apply some potential 0.3 volt. Then your CC cycling reaction will be converted to ECC reaction and you will start getting the data, your measurement data. You will find how much target is there. So first CC, then ECC. That's why I'm telling. So what will be the starting material? Tell me now.
Sir, S R2 are confirmed the starting material, and for the cycling chemical part, it will be R1, I think.
No, it will be O1. It will be
How?
O1. Yeah. So why? See, so you are providing S. If target there, then you will get this ball. This is nanomaterial, suppose. Then you will get P, right? See, now this P will react with which material? With O1 or R1? With O1, right? Not R1. Am I correct?
Sir, if it reacts with O1, then how R1 will come into picture?
Yeah, see, O1 now, so you are supplying O1. So O1 converted to R1 because of P. Now this reaction stopped. So chemical reaction becomes stopped. That's why you have to apply some electrochemical potential. Now electrochemical reaction will help you to add this one. So this reaction now will start. Now electrochemical reaction start. It will now it come. So electrochemical reaction now convert the R1 to O1. Now the cycling is completed. So now O1 to R1. Now O1. So now see P will react with O1 and it will go to the R1, and P itself convert to Q. So how Q now can be converted to P? For that we need some R. So this is actually reducing agent. So R2 should be some reducing agent. Why? Because Q actually some higher oxidation state. So just think about which one reducing, which one oxidizing. So it becomes somewhat complicated, but if you can understand which one the oxidation oxidizes from, which one reduced from, it will be very simple. See, so you are applying some oxidation potential, right? Make it clear. You are applying some oxidation potential. Then which one oxidized from, which one reduced from? Tell me now. O1 or R1?
Sir, R1 is the oxidized form.
Oxidized form R1. No, this is the reduced form. Because you are applying oxidation potential, so it will release the electron. Right? R1 will release the electron, it will go to, so if it is oxidized form, means it is already higher oxidation state. So how will go more higher oxidation state, right? So this is basically zero state, this is basically plus state. See? Because it is releasing the electron, R releasing the electron, right? Make it clear. Is it okay? Or can I repeat?
Yes, sir. Okay, sir.
Right. So R is the reduced form. That's why it will release the electron. So that lower oxidation state is the reduced form. So lower 2, it will go to higher. Now, this higher oxidation state again will go to the lower oxidation state only if some lower oxidation state material present. So in this case, P is the basically 0 or lower oxidation state, right? Right?
Yes, sir.
So P is the lower oxidation state. So that lower oxidation state will react the higher oxidation state. So then P will be converted to higher oxidation state material. Right?
Yes.
Right? Hello? Is it clear? Hello. Is it clear? Q is the higher oxidation state.
Yes, sir. Yes, sir.
That's why R should be reducing agent, right? So why R should be reducing agent? Because reducing agent now will reduce this higher oxidation state and it will convert it to P, lower oxidation state. Okay, so you have to think about your starting material should be R should be reducing agent. So S should be somewhat some specific reagent so that it can react with this gold or something like label, and it will form some lower oxidation state material. Okay, and this one now it will react with higher oxidation state O1. That will be your starting material. Okay, so in the ECC redox cycling, that's why the starting material will be R2 S O1. Clear? Guys?
Yes, sir.
Okay, so when you will form a ECC based redox cycling some biosensor, so your starting material as it is 1, 2, and 3. So these 3 should not react together, right? What do you think? Right?
Yes, sir.
If they start reaction, then your background will be high because it is a starting material. And they are responsible for your background. These 3 are responsible for your background, right? So if they start reaction together, then your background will be high. Yeah. So like this way, when you will optimize some ECC based biosensor, you have to check basically they are reacting each other or not. If they are reacting each other, you have to eliminate that material. You cannot use. Right? You asked me already how we can choose the material like this way. If they react each other, you cannot use them. So that is one fundamental thing. Number one. Now number 2. Now I'll ask you and you can answer me. Number 2, this R2. This R2 is the starting material. S is the starting material. Q is starting material. If they react on the sensor surface, because you are applying some potential, right? Finally, because you don't know target is present or not in the biosensor, you don't know. So you have to just mix this reagent and you have to apply the potential. That's all. This is your duty. So when you are applying potential, so this starting material should not react on the sensor surface, right? So their reaction on the sensor surface should be slow. Clear? Right, guys?
Yes, sir.
That is one. Now come to the third point. This is second point. Tell me, if this R, and so this is the Q your intermediate, R is intermediate, right? So if this R react with no, this one, no, this is a lower oxygen state, right? So this R can react also with this O1, right? It can react with it, means there is some intra reaction also possible, right? Like R1 can react with the O1. This reaction also possible, right? So this reaction also should not be very fast. Otherwise, it should be formed because of P, not because of R. I'll show you some diagram basically. Means whatever responsible for your signal, that reaction should be very fast. Like this reaction should be fast, this reaction should be fast, this reaction should be fast. So number 1, number 2, number 3, this reaction should be fast. But this R2 should not react on the electrode surface very fast, so that your background can be increased. Your S should not react on the electrode surface very fast, so that your background can be increased. Your O1 should not react on the surface very fast, otherwise your background will be increased. Clear? Guys, students, very important topic I am teaching you today. How to choose the chemicals for your biosensor. Okay, guys? Hello? Okay, everything fine?
Yes, sir. Everything.
Okay.
Yes, sir.
Okay, so let's give you, I think today I'm teaching so many new things. So let's give you one more example, then I will stop. See here, let me know, then first tell me. So this is a kind of the bios, see, I'm going to tell you first. So this is a full biosensor. So this is the primary antibody. This is PSA, means target. This is your secondary antibody that conjugated with gold nanoparticles. So tell me here, what is the starting material of this biosensor? Tell me the starting material of this biosensor.
NP,
NP,
NaBH4,
NaBH4, and one more. One more.
and then
Good.
ferrocene.
Good. FC plus. Yeah, FC
Yes.
plus means ferrocene. This one. Very good. So this is your starting material. Okay. Okay. Tell me now. Tell me the step by step. Which one chemical? Which one electrochemical? Tell me. I'm going to tell you. Number 1, number 2, and number 3. Tell me. Number 1.
Electrochemical.
No. Number 1
Sir,
only.
chemical, sir. Sorry.
Chemical.
Number 2 chemical. Number 3.
Chemical.
Number
Electrochemical.
3, electrochemical. So electrochemical means E, chemical means C, chemical means C. So it is, what is the name?
ECC.
So this is ECC reaction. So in this ECC based biosensor case, we are using some material. Now I'm showing you some material name. So actually we already found in our lab NP. NP means nitrophenol. This is the structure. No, this is aminophenol. This is amine group already converted. So NP means when here NO2 group, nitro group here. That is called nitrophenol. So this nitrophenol on the electrode surface, this reaction is very slow. We already saw this one. So this reaction rate only nitrophenol on the surface is very, very slow. You will not get very high current. Okay. Now, this nitrophenol and sodium borohydride, this reaction also very slow, almost no. Only this reaction possible if gold nanoparticle present. That is, I already told you, right? So gold nanoparticle here helping as a catalyst, not electrocatalyst. This is only catalyst. So this, so I am going to tell you here two catalysts, right? So here gold is the catalyst, and here ITO is the electrocatalyst, right? Here ITO, indium tin oxide nanoparticle, is the electrocatalyst, and here gold only catalyst. Now, if you put here gold on the sensing surface, then gold become electrocatalyst. Clear? Clear?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, very good. So we found that this nitrophenol, this reaction is very slow, and sodium borohydride and this nitrophenol reaction, this one also very slow. And nitrophenol, sodium borohydride, if you mix together with ferrocene flask, this is starting material, that is also very slow reaction. So how we can make the very fast reaction then? So you can make this fast reaction if only gold nanoparticle present. So this gold nanoparticle, with the help of sodium borohydride, basically it will be converted to aminophenol. Now this aminophenol, I mean this structure amine. So if there is NO2 group, then slow reaction. If amine group, then fast reaction. So this material you can choose. So this amine group, now it can react with this ferrocene flask very fast. So this reaction actually very fast. So if this reaction becomes slow, your signal will be very, very low. So to make a very high signal, this aminophenol product that it got from the nitrophenol by the help of gold nanoparticle, it should react with your electron mediator very fast. Then only aminophenol will be converted to quinonimine, QI. QI means quinonimine. I mean, it is something like this. So it will be oxidized like this, quinonimine. Something like this, it will be converted. So this is the oxidized product. Okay, so this quinonimine will be formed. Okay, so now aminophenol converted to quinonimine. Now quinonimine can be converted again aminophenol. How? By the help of reducing agent, sodium borohydride. You have already. So now if you apply some potential here, because your ferrocene plus already converted ferrocene, that is zero stage, this is plus stage. So zero stage means lower oxidation stage, it will release the electron, and that electron you can measure. So because of this cyclic reaction, you will get very high, very, very high signal. And because of your starting material, they are reacting slow on your surface, your background low. So basically you are making high signal because of ECC redox cycling, and you are getting low background because of your choice of the starting material. Clear, right? You are getting lower background because of your choice, because you are choosing such a material, they are reacting on the surface very slow, and you are getting high signal because you are using ECC redox cycling. Right, guys?
Yes, sir.
So that's why you will get a ultra sensitive biosensor. Your signal will be very, very high. See here. So this is your full reaction. So this is one chemical we can choose. We can choose so many chemicals like this way. Let's leave it today. Today I will not show you many things. Let's stop it. Next class I will show you similar kind of the chemical. How we can choose. Here one example, just NP, nitrophenol. So this is the nitrophenol one example. Yeah, we can use some other chemical. We can use some other mediator. We can use some other reducing agent. So that kind of starting material I will teach you again next class. Okay. How is this design, guys? Is it interesting?
Yes, sir.
Yes, sir.
Yes, sir.
Yeah. So like this way,